Okay, so good evening, everyone, and I welcome you all to today's live session. We are in the week 6 live session for the course Nonlinear Vibration, NOC25 me57, and this course is being taught by Professor S.K. Dwivedi, IIT Guwahati, and I'm Rashia Didi Ranjan, NPTEL PMRF TA from the Department of Mechanical Engineering, IIT Patna. So we have already done five actually. This one is the sixth, 5 live sessions wherein we have discussed the questions which would be helpful for you for solving the assignment problems. And so coming on to the overview of this, what has been taught in this week. I think that my screen is lagging. Okay, now I think it's fine. Okay, now it's fine. Okay, coming on to the overview of what has been discussed in this week's lectures. So these are the topics that have been discussed, I think. And so initially it was about the types of damping. What are the types of damping that a system encounters or has the or can have? So yeah, like for example, there is viscous damping, there is Coulomb damping, and it was discussed that what would be the equations and how the variation of the transient is going to happen, right, in case of different types of damping. Then there was discussion about the modal analysis. So, in case of linear system, the modal analysis is essentially important because, for example, if we have a 2 degree of freedom system, okay, and both the equations are coupled, okay, like for example, we have 2 degrees of freedom like x and y, and then we write the equations of x dot, y dot, or x double dot, y double dot. In that case, these equations are going to have the terms of x as well as y. Okay, so in case we want that we have a solution that would be, independent, or we should have an equation that is independent, like in terms of x, we have only terms of x and it is independent of y, something of that sort. So in that case, we use modal analysis. What do? We basically do some matrix manipulation, and on the basis of that we try to decouple the equation, and once the equations are decoupled it becomes easier for us to solve the equations, right? So in case of linear system it was very helpful, but now we have come to the non-linear system, and in case of non-linear system writing the equations in a generalized matrix form is a bit difficult. So however, what we can do is we can take the nonlinear term and consider it in the force matrix, right? So then in that case we can write our equation as mx double dot plus kx dot, should be c Cx dot plus Kx is equals to F, and this F is going to take care of all the nonlinear terms present in the equation of motion, right? Okay, after that, the discussion was about bifurcation. Okay, so in this case, what happened that instead, like earlier, we also discussed about bifurcation, right? And we discussed about only three types of bifurcation, which was the saddle node bifurcation, transcritical bifurcation, and pitchfork bifurcation. Okay, so those were actually static case of bifurcation. Now, static bifurcation essentially means that, see, for a system, we have a dynamic response and then we have a static response, right? Static response means what? Static response means that as the time progresses, the system actually attains a equilibrium point. It attains a equilibrium state, and corresponding to that equilibrium state, it is not going to go anywhere until and unless any external force is applied on it, right? Now, for that system only, if I remove the damping, okay, if I remove the damping, or when the damping is present, I give some kind of a excitation, external excitation, parametric excitation, any of such kind of excitation. In that case, the system will keep on vibrating. It can show periodic motion, quasi-periodic motion, chaotic, any kind of a motion. So these are the two cases, static and dynamic. Okay. So in case of static bifurcation, what happens is we are concerned about the equilibrium points or the fixed points, right? So in case of static bifurcation, we are concerned about how my equilibrium point or my fixed point is actually changing with respect to the parameter that I am considering, right? For example, I take a parameter, I change that parameter, and now I see that how my equilibrium points are changing. So that is the case of static bifurcation. Now, in case of dynamic bifurcation, what happens is that I see that after changing the parameter, is my system going to a periodic response, or maybe it is going from a periodic response to a static response, something of that kind. Then we call it a dynamic bifurcation case. Like, and then there is discontinuous bifurcation also, right? Where when there is jump or anything of such kind, and it is usually catastrophic in nature, right? So bifurcation was first discussed, different type of bifurcation. How can we know mathematically that which kind of a bifurcation is going to occur? Okay. Then types of fixed point, it was discussed. Like for example, the fixed point is a center, the fixed point is a stable point, saddle point, no, stable node or saddle point, or if it is a spiral in, spiral out, or that sort of things were discussed, that on the basis of eigenvalues, if I see the eigenvalues of my system, then how can I say which kind of a fixed point my system is having, right? So that was discussed, and then basin of attraction was discussed. You know, typically it was discussed through a graph, if you remember, that what was happening was there were two stable fixed points, and if we simulate the system for different initial conditions, what are we going to get? We are going to get that for a particular set of initial conditions, my system is always going to converge to the first fixed point, and for another particular set of initial condition, it is going to converge to the second equilibrium point, right? So when I'm changing the initial conditions, where my system is going, if I plot it on on a phase plane, then I will get to know, okay, this is how it is, and that I call as a basin of attraction. Okay, so all these things were discussed, and so I have taken the questions which would be helpful for solving the assignment problems. Okay, so okay, before that, I'll try to give a brief discussion about bifurcation. Although we have already done about the static bifurcation case, but I will try to give a brief idea, because then we'll take up the questions in that form. Right, because earlier when we were doing bifurcation, if you remember, that time I taught you that we will just plot the velocity and the position diagram, and on the basis of that we are going to say that, okay, this is a stable fixed point or an unstable fixed point, that sort of things we were doing, right? But now what we will do, we will use the Jacobian. Actually, we will use the concept of Jacobian and eigenvalues, and that we are going to use in order to find out that whether my fixed point is a stable fixed point, or it is a unstable fixed point, it is a source, it is a sink, it is saddle, and everything of that sort. Okay, so if you remember, I gave this example of buckling of a beam. We had a mass and we had a beam like this, right? So this was in an equilibrium state, right? Now when this mass was increased from M to capital M, this beam led to what? Buckling, like this or like this. It is going to have either of the two positions, right? So this is what? This is the, okay, I'll just make two different figures. Either this or this. Okay, the beam is going to buckle either like this or like this. Okay, so what was happening? For this mass, I had only one equilibrium state of the beam. Okay, but for this mass, I have two equilibrium states, and the system can attain any of the two, and it will depend upon various factors like initial condition, depending upon the inertia, what is the moment of inertia of the beam, how the mass is placed, and many other things. Okay, but it can attain any of the two. So what did I do? I just changed the mass. I didn't change any property of the system. I didn't change any geometrical property of the beam. Anything I didn't change. I just changed the mass. I just changed the load. Okay, and corresponding to that, the equilibrium state is going to change. Now here I call mass as a parameter, right? So with the variation of parameter, the number and the type of equilibrium point actually changed for my system. Okay, and from here comes the concept of bifurcation, right? So we discussed about different kind of bifurcations, right? First one, if you remember, was the saddle node bifurcation. First one was the saddle node bifurcation. If you remember its equation, it was something of this type: x dot is equals to r plus x square, where r was my what? It was my parameter. Okay, so if you see over here, I have two fixed points, and those fixed points are nothing but plus minus under root of minus r. Okay, so if you see, this fixed point will exist only if r is less than 0. There is again some lag in my system. Yeah, it is fine now. Okay, so now this equilibrium point is only going to exist for r when it is negative. Okay, for positive r, it is not going to exist. So if you see, it's a kind of a saddle node bifurcation. And if you further see, with the help of Jacobian, or if you plot the velocity profile, you're going to get that among these two equilibrium points, one is stable and the other one is unstable, right? So when you plot it, you will get to know that, okay, one was stable, one was unstable. You can plot the velocity profile, or what you can do is you can use the Jacobian as well. Okay. Maybe I'll just use the Jacobian only. Jacobian is equal to nothing but twice of x, right? So for plus under root minus r, it is going to be unstable because the eigenvalue is going to be positive, and for minus of under root of minus r, it is going to be stable, right? So what I can do is now I can plot the bifurcation diagram. Okay, so this is my r axis, this is my x axis. Now I plot what? X in terms of r. So then I see this one is stable, this one is unstable. This is going to be my plot. Okay, and for r greater than 0, I just don't have any of the equilibrium point. So this was my saddle node bifurcation. Second was my There is some lag. Anyways, I'll continue. Second was the transcritical bifurcation, if you remember. So in case of transcritical bifurcation, essentially my equation of motion was nothing but Rx minus x square. Okay, so now if you'll see in this case, if I want to find the fixed points, it is going to be nothing but I'll take x as common, x0 and r. These are going to be my two fixed points, or you can say equilibrium points. Stability we'll talk about after finding out the Jacobian. So these are the two fixed points. If I want to find the Jacobian, it is going to be nothing but r minus twice of x. And if I want to find out the eigenvalue, so lambda at x0 is going to be nothing but r, and lambda at okay. So if you'll see that if my r is less than 0, in that case x is equals to 0 is what? Stable. And when r becomes greater than 0, my x is equals to 0, 0 becomes unstable. Similarly, for this, there is an opposite kind of a variation. For lambda at x is equals to r, there is an opposite trend, which means that for my x or for my r, when it is less than 0, my x is equals to r is what? It is unstable. And as soon as it becomes greater than 0, it becomes stable, right? Because it becomes negative. So if I plot, this will be my x-axis, this will be my r-axis. This is stable, this is unstable, this is stable, and this is unstable, right? So this is going to be the variation. Okay, so this was my transcritical bifurcation. Second, if I'll talk about the third one, if I talk about which was the pitchfork bifurcation, it was essentially of two different types. One was the supercritical, another one was the subcritical. Right, so among them, if you remember, the equations had a third algebraic power, right? The if I talk about first supercritical, so the equation was nothing but right. This was the equation. If I want to find out the fixed point, what is going to be? I'll take x as common. R minus x square is equals to 0. So I'll have x is equals to 0 and x is equals to plus minus under root of r. Okay. And now if I want to find the Jacobian, it is nothing but r minus 3 times of x square, correct? So we'll just write the eigenvalue at x is equals to 0 is nothing but r, correct? Eigenvalue at x is equals to plus under root of r is going to be r minus 3 times of sorry, 3 times of r minus 2r, and you'll see that the eigenvalue at x is equals to minus of under root r is also nothing but minus of 2r, correct? So essentially both the plus of under root of r and minus of under root of r, both these fixed points are either going to be stable or either going to be unstable because both have the same eigenvalue, right? Okay, so now if I try to plot it, how is it going to be? So you know now, here the eigenvalue is r. So for r less than 0, x is going to be stable. For r greater than 0, x is going to be x0 is going to be unstable. Similarly, for x plus of under root r and x or minus of under root r, what is going to happen? So for r less than 0, these both are going to be what? These both are going to be unstable, and for r greater than 0, these both are going to be. Anyways, there is no question, because this, if you see, it is my under root of r. So for r less than 0, these both roots are not even going to exist. So talking about its stability is actually wrong. Okay. So it will exist only for r greater than 0, and for r greater than 0, both of them are going to be stable. So if now I try to plot it, it will be something like this. This will be my r axis, this will be my x axis, and so this is stable, 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 and this becomes unstable. Okay, so this is nothing but my supercritical pitchfork bifurcation. Okay, A, and B is going to be subcritical. Subcritical pitchfork bifurcation, which has x dot is equals to xr plus x cube. Nothing different, just a change of positive sign. Okay, so if here I try to find out the fixed points, it will be nothing but r plus x square is equals to 0. I'll have x is equals to r and x is equals to plus minus under root of minus r. I have a minus r over here, correct? So now what happens is these two roots are just going to exist only if r is less than 0. For r greater than 0, it is not going to exist, so it will exist for r less than 0. Further, if I try to find out the Jacobian, so the eigenvalue at x is equals to 0 is going to be what? R, correct? It is going to be nothing but R. Okay, my system is again lagging because I cannot see. Okay, it's fine now. Okay, yeah. So this is what is going to be, right, for the subcritical case, and my eigenvalue is going to be nothing but R, right, for x0 and lambda at, let us say, plus minus of R is going to be nothing but R plus 3. Okay. So now here if you see, my these both the fixed points are going to exist only if r is less than 0. But for r less than 0, this becomes positive, right? My eigenvalue becomes positive, which means that both the fixed points are nothing but unstable, right? They are unstable fixed points, right? But if you see for x is equals to 0, here my if my r is less than 0, x is equals to 0 is a stable fixed point. If my r becomes greater than 0, then it becomes an unstable fixed point, right? So how the plot is going to be, if I plot the x-axis and the r-axis, one is again stable over here. It is unstable for r greater than 0, right? And if I talk about these both points, it's going to be something like this, because you see they are going to exist only for r less than 0, and they are unstable because we have the eigenvalues minus of 2r, and if I put a negative value of r over here, it becomes positive and hence is unstable, right? So this is how the variation is going to be. Now if you see all the three bifurcations that I have discussed over here, these three are the uh, very main cases of static bifurcation, right? These are the cases of static bifurcation, which means we are actually concerned about the variation of the equilibrium points corresponding to the change of the parameters, correct? So yes, but now if I talk about other bifurcations, So I have bifurcation as static and dynamic. Static bifurcation has saddle node, then it has transcritical, and then it has pitchfork, which further has supercritical and subcritical, correct? And the dynamic bifurcation is going to have hop bifurcation, right? And the discussion about hop bifurcation has already been done in the lectures. However, when we will take up the question about it, we will do the brief discussion. Okay, so these three type of bifurcation I have already briefly explained. Again, just for the revision also, and for showing that earlier when we discussed about these kind of bifurcations, we actually quantized the stability on the basis of the plot, on the basis of the plot, that how my x dot is varying with respect to x. Okay, if it is in the positive direction, the system is going to go towards the x direction. If it is in the negative direction, it is going to go towards the left side. And if there is convergence from both the direction at a particular fixed point, then it is stable. If there is divergence, it is unstable. But here what we did, we used actually Jacobian in order to find out the stability of the fixed points, right? So it gave us a second perspective. Okay, now we'll take up the questions basis of that. Okay, so the first question says, for the equation of motion, which of the following is incorrect? So, okay, stable, unstable. So we are actually concerned about the type of bifurcation that is occurring here. So again, we will first write down the equation of motion. So the first thing that we are going to do is find the fixed points. How are we going to find the fixed points? We'll put x naught is equals to 0, which implies 1 plus rx plus x square is equal to 0. So this is the quadratic equation. What we are going to do, we know that the roots of the quadratic equation is going to be what? X naught is going to be minus b plus minus, maybe I'll write it somewhere. If you remember, for this, we had the value of root as minus b plus minus under root of b square minus 4ac divided by 2a, right? So using that only we are going to do it. So minus b plus minus under root of b square minus 4 into a into c, which is going to be 4 only, divided by 2. So essentially my equilibrium points are going to be minus 2 plus minus r square minus 4 divided by 2. Okay, so you see my fixed point is always going to be real. It cannot be imaginary, right? Because physically it is not possible. If we are working with complex numbers, complex equation, then that's a different thing. But talking about a physical system, complex roots means the roots are not going to exist, right? So since here is a under root of this term, okay, so this should always be positive for the root to exist, right? So we will apply the condition r square minus 4 should always be greater than 0, right? So what are we going to have? We are going to have r square should be greater than 4. Okay, so this is going to give us nothing but r should be less than minus 2 and it should be greater than 2. You'll see that only if this condition is satisfied, then only these two fixed points are going to exist. Otherwise, my fixed points are not going to exist. Correct? R should be greater than 2 and R should be less than minus 2. And there can be an equality as well, no doubt. Okay, but if it is in between minus 2 and 2, definitely the roots are not going to exist. Okay, so we'll write the fixed point exists only for these values of R. Okay, I hope this is clear. Okay, now what we are going to do, now we are going to find out about the stability. We have known that okay, these are the roots. They are going to be two roots, and it is going to exist only for the range of these values of R in between -2 and 2, not including -2 and 2. There are going to be no roots, and at -2 and at 2, there is going to be only one root, right? That will be minus of R by 2. Now, if I talk about the stability, for that we have to find out the Jacobian, which is nothing but d of f divided by dx, which will be R plus twice of x, right? Now, if I put the value of x over here, so if I want to find out the eigenvalues, for the eigenvalues, for the eigenvalues, if you remember, we had the Jacobian matrix, we did minus of lambda I, we computed the determinant and made it equal to 0. Here, my Jacobian matrix is nothing but R plus 2x, it's a 1 cross 1 matrix. So, in that case, I have R plus 2x minus lambda is equals to 0. So, lambda is going to be nothing but R plus 2x. Whatever is my Jacobian, if I put the value of x in it, that is going to give me directly the eigenvalue. Okay, so I'll first compute the first eigenvalue, which is at minus of R by 2 plus under root of R square minus 4 by 2. What is it going to be? R plus twice of minus R by 2, this. Okay, so you'll see this and this will get cancelled. So we are going to have nothing but under root of R square minus 4, which is positive, right? Which is positive. Okay, so but this root is actually unstable. This root is unstable because my eigenvalue is positive. Now if I compute the second eigenvalue, which is at what is it going to be? We had R plus 2x. Okay, so we'll have an R plus 2 into R, and R will get cancelled. So we are essentially going to have minus of. Okay, so my this root is what? Since my eigenvalue is negative, it means this is a stable fixed point, right? So what do I get to know? I get to know that okay, I'm going to have two fixed points, and one is going to be stable, another one is going to be stable. However, there is one more thing that needs to be there in the mind, that these two roots are only going to exist for certain uh, values of R, right? It is not there for all the values of R. Okay, so if you see that in between -2 and 2, there is no fixed points. And at, let us say at 2, there is occurrence of a fixed point. Okay, sudden occurrence of a fixed point which further diverges into two fixed points. Out of them, one is stable and the other one is unstable. So if you remember, this is nothing but a typical case of a saddle node bifurcation. Correct? This is a typical case of a saddle node bifurcation. If you remember, in saddle node bifurcation, this was happening now. We had two fixed points, out of which one was stable, another was one was unstable, and these two fixed points existed only for a certain value of the bifurcation parameter, right? For the other values, there was no fixed point. There were no fixed points, and out of the blue in the sky, uh, suddenly a fixed point appears. Okay, half stable fixed point diverges into two fixed points in which one is unstable, other one is stable. That is what the case is happening. But if you'll see over here, two saddle node bifurcations are happening. Two are happening. One is happening at -2 and the other one is happening at 2. So what I'll do is, if I go from the negative axis towards the positive axis, what I see is that initially I have two equilibrium points. Okay, they come together, converge, and the fixed points disappear. Further, when I go from -2 towards 2, there is occurrence of a half stable fixed point which further diverges into two fixed points, out of which one is stable and the other one is unstable. Correct? So that is what is going to happen, right? So there are two. So in one case, the saddle node bifurcation actually leads to the occurrence of two fixed points, and in the other case, the two fixed points come together and disappears, right? Both are the case of saddle node bifurcation. I hope this is clear. So we'll see the options now. System has one stable and one unstable equilibrium point for r less than -2. Okay, we have to see which one is incorrect. Okay. System has one stable and one unstable equilibrium point for r less than -2, right? This is the correct point, right? We already did it here. Okay, system has one stable and one unstable equilibrium point for r greater than 2. This is also true. So system has one stable and one unstable equilibrium point for r greater than 0. Well, this is the incorrect option, right? Because for r greater than 0, it is not true. It is only true for r if it is greater than 2 and less than -2. Okay. So this is going to be the correct option. And the D option is saddle node bifurcation occur here. Yes, it is true. Saddle node bifurcation is occurring. Both are the case of saddle node bifurcation. In one case, we have two equilibrium points coming together, okay, and then disappearing. And in the second case, we have a sudden occurrence of a half stable fixed point and then further divergence of both. Okay, I hope this is clear. Now we'll go to the second question. Okay, so the second question says for the equation of motion,
Ma'am, I have a doubt.
yes,
Ma'am, can you explain why the system is stable if we have a negative real eigenvalues?
okay. See, actually, this comes from a basic concept of differential equations, if you remember. I discussed it in the previous live session also. Uh, so I discussed that like for a two-dimensional system, my eigenvalues are essentially eigendirections and eigenvalues. So what happens in the eigendirection, like for example, if I have a system of this form, okay, so my eigenvalue actually helps me to write this as nothing but lambda into xv. Lambda is nothing but a scalar matrix and xv is my eigendirection. Okay, so what happens is that when my system is in the eigen direction, what happens is that I can relate x dot with x by nothing but a constant value. Okay, so if you remember that for a system, if I have something like x dot is equals to minus 7x, I can easily integrate it. I can write dx by dt equals to minus 7x. So dx by x is equals to minus 7 dt. If I integrate on both sides, I'll have ln of x is equals to minus 7 of t. So x I'm going to have e to the power minus 7t. If you see, as t tends to infinity, what is going to happen? If t tends to infinity, my x, where is it going to go? It is going to converge to a, it is going to converge to a particular value, right? Am I audible? Hello?
Yes, ma'am. You are audible. Yes,
Okay,
ma'am.
but
You are audible.
my screen is having some lag because it is, yeah, now it has come. Okay, so as t tends to infinity, my x is going to converge, you know. However, if it would have been x dot is equals to 7x, my solution would be nothing but e to the power 70. Here, if t tends to infinity, x tends to infinity. Exponentially, it is going to grow, right? Exponentially, it is going to grow. So essentially, my eigenvalue are those values which tends to relate my eigendirection with the velocity, right? Here, like -7 is the eigenvalue, here 7 is the eigenvalue. So you can see for the negative value of eigenvalue, what has happened? My system is converging, right? But for the positive value of eigenvalue, it is diverging, right? That is why we say that in case of positive values, it is going to diverge because then the equation are going to have a positive exponential power. But for the case when we have a negative eigenvalue, my system is going to have a negative exponential, which means it is going to converge. Okay, I hope this is clear. And if it is not clear, have you seen the previous week's live session?
Okay, ma'am. It is clear now. Thank you.
Okay, but please go through the previous week's live session because there I have discussed it very thoroughly. Okay, I've made the
Okay.
graph also that how the stability is going to change and what kind of stabilities can occur. Okay, it will be helpful for you.
Okay, ma'am. Thank you.
Okay, so we'll be coming on to the second question. Okay, so we have this equation. Now, if I want to find out the fixed point, what will I do? I will put x dot is equals to 0, which implies, so I'll have x is equals to 0 and x is equals to r minus 1 by r. These are going to be my two fixed points. Okay. Now I have to talk about the stability. Again, what am I going to do? I'm going to calculate the Jacobian. So I'll
Ma'am, I have
differentiate.
one more doubt, if you don't mind.
Yes.
Ma'am, why we calculate the Jacobian matrix in this type of questions or this type of problems?
Hmm. It means you have not attended the previous week's session, right?
Yes, ma'am.
Yes. Uh, okay, let's do one thing. Can you attend first, see it, if possible? Because it is going to be a very long discussion. I have discussed it in the,
Okay, ma'am. I will go through that video,
yeah, yeah.
and in
You
next
just go
session
through
I will
that.
ask her.
Yeah, exactly what I was going to say. We just go through those 15-20 minutes with the fast forwarding. You listen to it. If you have any doubts, still you have any doubt, then you can ask me in the next session.
Okay, ma'am. Okay.
Okay? Because
Thank you.
there I have actually told about why the Jacobian is required. What is the use of
Okay, ma'am.
Jacobian?
Okay.
Okay,
Thank you.
okay. So let us compute the Jacobian, which is nothing but the differentiation of my function with respect to x. Let us assume this is f. So what is it going to be? It is going to be 1 minus r plus twice of rx. Okay. So, okay. So at x is equals to 0, my eigenvalue is going to be what? If you'll see, if I'll put x is equals to 0, I'll have 1 minus r. So the stability of x is equals to 0, what is going to happen? It will depend on what? The value of r. Yes. If my eigenvalue lambda 1 is negative, my x is equals to 0 is stable. If it is positive, my x is equals to 0 is unstable. Okay. So if I have lambda 1 which is equals to 1 minus r less than 0, what is going to happen? R should be greater than 1. Okay. So if my r is greater than 1, then x is equals to 0 is what? I'll just write it. If r is greater than 1, x is equals to 0 is stable. If r is less than 1, x is equals to 0 is unstable. I hope this is clear. This is also, you can see directly also, right? Like if my r is less than 0, what is going to happen? It is going to be, okay, wait. This should be unstable. And this is stable. I've written the opposite actually. Yes. So because here I have applied the condition less than 0, less than 0 means for the stability. So if r is greater than 0, what is going to happen? It is going to be, no wait. Yeah. So you see over here, I have taken the condition that it should be less than 0. Less than 0 means what? If it is less than 0, then it simply means that my eigenvalue is negative. So if my eigenvalue is negative, what is going to happen? My system is going to be stable, correct? So if I take r over there, I'll have r greater than 1, right? So if my r is greater than 1, which means minus 2, sorry, 2, 3, 5, anything. So 1 minus something bigger than this is going to be negative, right? So for r greater than 1, it is going to be stable, right? And if I take r which is less than 1, maybe we'll say 0.5, then my eigenvalue is going to be 0.5. Or if I take something negative, some negative value, minus 5, minus 4, it is going to be positive value. So it is going to be unstable, right? So now I know the variation of x. Okay. Firstly, my critical value of parameter RC is what? 1. That is what I have to remember for plotting. Okay. Now I'll come to the second point, my second equilibrium point. Okay. So if I compute the eigenvalue 2, which is at x is equals to r minus 1 by r. Okay. So what is it going to be? If I put it in this Jacobian equation, what is it going to be? It is going to be 1 minus r plus 2r, r minus 1 by r. R will get cancelled. I'll have 1 minus r plus 2r minus 2, which is going to be nothing but r minus 1. Okay. If you see, this is exactly negative of what I got in the case of x is equals to 0, right? The eigenvalue that I got over here is actually opposite of what I got. This is actually minus of lambda 1. Just a second. Okay. So if you see, my lambda 2 exactly negative of lambda 1. So it is going to have a characteristic negative 2 or opposite to what we had for lambda 1. Okay, for now we'll just forget this one and we'll again try to see that okay, my this fixed point x2, how is it going to vary? Let us see. Okay, so I'll just add one more slide. So I have lambda 2 is equals to r minus 1. So if I now want my x2 to be stable, my lambda 2 should be less than 0 or my r should be less than 1, right? So x2, which is nothing but r minus 1 by r, and unstable for r greater than 1. Okay, so if you see the stability of x1 with r and x2 with r is actually somewhat opposite, because you see for r greater than 1 my x0 was stable, but here for r greater than 1, you see this one is unstable, right? So there is an opposite characteristic and there are two fixed points. So if you remember that for transcritical bifurcation we plotted something like this. We had two fixed points which had something of this kind of behavior. I had two fixed points, and at the critical value RC, it was actually changing the stability. There were two values, na, x1 and x2. Initially, one was unstable, the second one was stable. As soon as they both crosses the critical value of the parameter, x1 now becomes stable and x2 becomes unstable. This is what is happening over here. I have two fixed points. One is r minus 1 by r, uh, yeah, r minus 1 by r, and the other one is 0. So you see, 0 is like stable. No, it is initially unstable. Yeah. For r less than 0, 0 is unstable and r minus 1 by r is stable. As soon as it crosses r is equals to 1, what is going to happen? The stability is going to change. Okay, it is going to change with itself, and r minus 1 by r becomes unstable and 0 becomes stable, right? So this is a case of, I'll just write it. This is a case of transcritical bifurcation. Okay, so we'll now come on to the options that we are having. So we have system has two stable fixed point for r greater than 0. This is not true because it is not having two stable points, fixed points together, right? One is stable, other one is stable. The first becomes unstable, second one becomes stable. That is happening. So this is incorrect, and so this is going to be the correct option, because if you see in the question, it is asking which one is incorrect. So this is incorrect, and that is why this is the correct answer. Okay. System has no stable fixed point for r greater than 1. So this is not true, and hence this is a correct option. X is equals to 0 is stable for r greater than 0. X is equals to 0 is stable for r greater than 0. No, this is not true, because here we have already found out that x is equals to 0 is stable only for r greater than 1. So this is not true. And the last option says saddle node bifurcation does not occur here. Well, this is true. The statement is true corresponding to what has been given, but since we have to find out which one is incorrect, so this is not going to be the option that we are going to select, because saddle node bifurcation is actually not occurring here. Here transcritical bifurcation is occurring, right? So the first three options are correct. Okay, coming on to the third question. Okay. For the equation of motion, which of the following is incorrect? Okay. Again, doing the same thing which we are doing since the last two questions. First, we'll find out the fixed point. How? We'll put this is equals to 0. We'll take x as common. So we'll have r plus 4x square equals to 0. So the first fixed point is going to be 0. And the second fixed point is going to be uh, x square is going to be minus of r by 4, which implies x is going to be plus minus under root of minus r by 2. Okay. So we have x1, 0, x2, and x3 minus, and this is with a plus. These are my three fixed points. Okay. Now we'll have to talk about the stability. So we'll switch to the Jacobian, which is nothing but okay. This is going to be nothing but r plus 12 x square. Correct? Now what will I do? First I will find out the stability of 0. So for x1, which is 0, my eigenvalue is going to be r. My eigenvalue is going to be r. So as the value of r changes, the stability changes. So my x1 is stable for r less than 0, and unstable for r greater than 0. Obviously, because for less than 0, the eigenvalue is negative, stable. For greater than 0, eigenvalue positive, unstable. Simple. Coming on to x2. For x2, which is minus of under root of minus r by 4. Okay, first thing, I'll write it over here also. X2 and x3 are only going to exist for r less than 0. Yes, because we have minus of r and then we have a under root. So only if the value which is inside the under root, if it is positive, then only we are going to get a real fixed point. Otherwise, the fixed points are going to be imaginary, which makes no sense. Okay. So for this, if I want to find out that how the stability is going to be, we'll have lambda 2 is equals to r plus 12 into, here it is going to be 2 and not 4. 2, correct? Yeah. Here also 2 whole square. So we'll have r plus 12 into r by 4, which is going to be nothing but 4r, right? This is going to be 4r. So see, already my r has to be what? It has to be negative. Then only it is going to exist now, right? It has to be negative. And if I see the eigenvalues, wait, now r plus 12 x square minus and plus, and then we are going to have a square. Hmm. Okay, so this is what I'm doing wrong. Here should be a minus now. Yes. Why? Because when we are squaring, this minus is going to get positive, but the minus which is inside the under root is going to stay over there, right? So we are going to have minus r minus of 3r. We are going to have minus 2r over here, right? The negative sign. So if you see that my this x2 and x3, firstly, for x2 and for x3, for both of them, we are going to have the same eigenvalue. We are going to have lambda 3 is equals to lambda 2. If you'll ask me why, because we have a square term over here. We have 12x square. So when we are doing x square, so it is always going to be the same value, right? Secondly, we have minus 2r. So both of these x2 and x3 are only going to exist for negative value of r. For negative value of r, lambda 2 and lambda 3 both are going to be positive, and hence x2 and x3, when it will exist, it will be unstable. So we'll have will be positive for r less than 0. If I try to plot it, it will be something like this, something like this, right? This is my r. This is nothing but 0. This is plus. Okay, so this is going to be the plot. So this is what? This is essentially a subcritical pitchfork bifurcation. Okay, so now we will look into the options. System has two stable fixed points for r greater than 0. Two stable fixed points for r greater than 0. This is incorrect. So this option is okay. So this is incorrect, and hence we will choose this option. System has no stable fixed points for r greater than 0. Well, this is true, right? For r greater than 0, we don't have any. Actually, we have a fixed point, which is 0, but it is not stable. Okay, so this is a correct statement. Okay, so we'll not choose it. Then third, system has one stable and one unstable equilibrium point for r greater than 0. This is incorrect. So we'll choose this option. Saddle node bifurcation occur here. This will also be chosen because this is the case of subcritical. Subcritical. This is a case of subcritical pitchfork bifurcation. Okay, I hope this is clear. Now we'll come to the question number 4. So question number 4 says the parameter mu of the system is varied, then it would result in hop bifurcation for which of the following? So firstly, we'll come to the concept. Uh, yeah. So firstly, we'll come to the concept of what is hop bifurcation? So if you remember, as it was discussed in the class, hop bifurcation essentially occurs when with the change of, firstly, it's a dynamic bifurcation, right? So when there is a change, when there is a change of a parameter, okay, and it results from maybe spiraling in to spiraling out behavior, okay, or there is actually, you know, occurrence of a periodic orbit, okay, a periodic orbit exists, okay, with a variation. If I if I vary the parameter and if I check how the eigenvalues are varying, so if I see that the eigenvalues are varying, they have an imaginary value and they vary from one imaginary value to another imaginary value as it changes from the left hand side to right hand side, then we say that okay, hop bifurcation has occurred. So for this kind of a question, see, we have in the class also we have already gone through that there are certain conditions. For example, if I have an equation and there are two, three conditions, if those conditions are satisfied, then I can conclude, okay, the hop bifurcation is occurring. Okay. But here I don't know what my system is. I don't have any of the equation which I can put up in those conditions and then see whether the hop bifurcation is occurring or not. So how am I going to see that, okay, what is happening? So if you remember that in case of hop bifurcation, among those conditions, there was the first condition which said that there should always be a pair of imaginary eigenvalues. And here we have already given the eigenvalues. Okay. So for the hop bifurcation to occur, it said that there should always be a pair of imaginary values. Right. So if on the basis of this only, if we are going to see the options, we know which is the one is the correct option. Right? We know that the option D is correct because for the first case there is no imaginary value. For the second case there is no imaginary value. For the third case, initially there is an imaginary value, but as soon as it crosses it, the system actually goes from an imaginary value of eigenvalue to a real value, right? But in case of hop bifurcation, the change, though there is a change, but there should be a one set of imaginary eigenvalues. So corresponding to that, option D is the correct option, right? But there is two, three things that I would like to mention over here. That first thing is that hop bifurcation actually leads to the occurrence of a periodic orbit, actually a limit cycle. Okay, and for a limit cycle to occur, if you remember, for a limit cycle to occur, what is the main thing? What should be the main thing in the eigenvalue? There should be the imaginary value, right? Because if you remember, when we talked about the stability in the previous week's live session, we said that, okay, if my eigenvalues are having imaginary values, imaginary set, then either I'm going to have spiraling in behavior, I'm going to have spiraling out behavior, right? And in between that, when my real part becomes 0 and I have only pure imaginary values, in that case, I'm going to have what? My fixed points will act as a center and my system is going to have periodic orbit, right? It is going to have periodic orbit because since there is no real value, so real value is equal to 0. If real value would have been positive, it would go outside spiraling out. If the real value is negative, it will come inside, which is spiraling in. Both will keep changing the amplitude. Okay, but if there is no real value, what is going to happen? I'm just going to have a sinusoidal kind of a variation with the same value of frequency and same value of amplitude until and unless obviously I don't change the initial condition. The same ideology is going to get over here also in case of a Hopf bifurcation. We should have some kind of imaginary eigenvalues, in order to have a uh, limit cycle to occur. Okay, so if you remember also in those where we discussed about the various rules, where sir discussed about various rules that has to be followed in order to conclude that okay, my system is having a Hopf bifurcation. The first one was that there should be a pair of imaginary values. Okay, and this is what it is showing. So option D is correct. Coming to question number 5, which of the following option gives the equilibrium point of the set of equation given as? So we have a set of equation, we have to find what? Nothing but the equilibrium point. So if you see, this is not a linear equation, this is actually a nonlinear system, but it is a kind of nonlinear system which we can solve on our own. So we'll write x dot. What we'll do, we'll take x as common, because if you see in all the three terms, x is multiplied. We'll have 3 minus 2y minus x, and y dot. Similarly, we are going to take y as common, so we can write it as 3 minus 2x minus y, right? This is going to be my equation. Now, if I want to find out the equilibrium point, this will be equal to 0, this will be equal to 0. Okay, so for the first equation, either this is going to be 0 or this is going to be 0. Okay, so we'll have the first case first. Okay, we'll do let x is equals to 0. So if x is equals to 0, I consider that my second term is not equal to 0. So if my x is equals to 0, and if I take the help of the second equation and I assume, see, in the first equation, x equals can be 0 and the multiplication can be 0. In the second equation, this can be 0 or this can be 0. So I'll first consider let x is equals to 0. Then for the second equation, I can have y is equals to 0, or I can have 3 minus 2x minus y is equals to 0. So if I'll consider y is equals to 0. From equation 2, let us consider 1, 2. So my first equilibrium point is going to be 0, 0. Second equilibrium point is going to come when I consider x 0, but now I consider 3 minus 2x minus y is equals to 0. Since I already know my x is equal to 0, so I'll just have 3 minus y is equals to 0, which will give me y is equals to 3. So my second equilibrium point is going to be 3. Similarly, if I now consider my y is equal to 0, so one option I already have x is equals to 0, and that I've already written as a fixed point, 0, 0 here. So I'll consider that okay, the multiplication, the second term is 0. 3 minus 2y minus x is equals to 0. Now since I've already considered my y 0, I'll just have 3 minus x is equals to 0, which implies x is equals to 3. So I'll have 3, 0. Okay. Now comes the option when both x is not equal to 0 and y is not equal to 0. So then what is going to happen? I have two equations, and these two equations are linear equations, so I'm going to solve it. Now I'll consider that okay, this is equal to 0 and this is equal to 0. Okay, so what I'll do, I'll just multiply it by 2 and apply a minus. Okay, what is it going to give me? It is going to give me 3 minus 2y minus x minus 6 plus 4x plus 2y is equals to 0. This will get cancelled, and so I'm going to have 3x minus 3 is equals to 0, x is equals to 1. And when I'll put it in this equation, I'll get 3 minus 2y minus 1, y is equals to 1. So my third equilibrium point is going to be 1 comma 1. I hope this was nothing but simple mathematics. So as you can see, all the options are correct. This was easy. Now when I come to the second question, it says discuss about the stability of the fixed point obtained in the previous question. First I'll write the fixed points 0, 0, 0, 3, 3, 0, 1, 1. I'll also write the equation again over here, which is nothing but 3x minus 2xy minus x square and y dot, which is equal to minus of y square. Okay. So now since we are talking about stability, what are we supposed to do? We'll now switch to the Jacobian. So for the Jacobian, we are going to write if this is f1, this is f2. And if you remember, we write Jacobian as 3 minus 2y minus 2x. I hope this is correct. This is going to be my Jacobian. Now, since I want to find about the stability, what am I going to do? I'm going to replace my x and y with the corresponding fixed points, find the eigenvalues, and then I can tell whether my fixed point is stable or unstable. So let x naught is equals to 0, 0. Then I'll have Jacobian as what? 3, 0, 0, 3. Okay. And if I do lambda I minus, I'm going to have what? 3 minus lambda 0, 0, 3 minus lambda. Now when I'll find out the determinant and make it equal to 0, I'm going to have my eigenvalues as 3, 3. Two eigenvalues, both are positive, which means my x0, x0 and y0 fixed points is actually unstable. So I'll write x naught is unstable. I'll come to the second fixed point for which I've considered as 0, 3. I'll have my Jacobian J2 as what? 3 minus 2y should be gone. 3 minus 2x, x. Okay. x5 is 0. So y, which is 3 minus 6 minus 3. Then I'll have minus 2x will be 0. Then minus 2y, which will be minus 6. And then we have 3, again minus 3. Right? This is going to be my Jacobian. Alright. Now if I want to find out the eigenvalues, which will be nothing but minus 3 minus lambda, determinant of 0 minus 6 minus 3 minus lambda. What I can do it, I can write it like this, taking the minus common. This will be nothing plus but 3 plus lambda whole square. is equals to 0, lambda is equals to minus 3 comma minus 3. So x1 is stable. Why? Because both the eigenvalues are negative. Now for x2, which is nothing but 3 comma 0, I'll have my Jacobian J3 as, it's going to be the same, I guess, because we'll have 3 minus 2y will go 2x, 3 minus 6, which will be minus 3. This is going to be minus 6 minus 2x. Then we'll have 0. And then we are going to have 3 minus 6, which will be minus 3. Okay. Now again, if I'll compute the Jacobian, what will it be? We'll have minus lambda 3 plus lambda square is equals to 0. So x2 is stable. And for x3, which is nothing but 1 comma 1, I have the Jacobian as 3 minus 2y minus 2x. So 3 minus 4, which is going to be minus 1. We have minus 2 minus 2 and minus 1. So for computing the Jacobian, we'll have minus lambda minus lambda. So if I take minus out and 1 plus lambda is common, what is going to happen? We are going to have 1 plus lambda. Yeah, 1 plus lambda square and 2 to 4 minus 4 is equals to 0. So 1 plus lambda square, sorry, should be a whole square equals to 4, which implies 1 plus lambda is equals to plus minus of 2. So lambda we are going to have minus 1 plus 2, 1 and minus 1 minus 2 minus 3. See, we have a positive eigenvalue and then we have a negative eigenvalue, which means that x3 is a saddle. If you remember, saddle was a point which had convergence from one direction and it had divergence from the other direction, as we discussed in the previous week's live session. So it is going to be saddle. Okay. Okay, coming on to question number 7. Which of the following bifurcation may be observed for this? Okay, same thing that we are doing. Although this is a nonlinear equation, so it is a bit difficult. So for finding out the fixed point, we'll put x dot is equals to 0, which implies mu minus, correct? This is what it is going to be. So first fixed point we are going to get from equating 1 plus x is equals to 0. So my first fixed point is going to be nothing but 1. Instead of writing x naught, we'll write x1 is going to be minus 1. Other fixed points we are going to have as x plus 1 whole square is equals to mu. X plus 1 is going to be plus minus under root of mu, and hence it is going to be minus 1 plus minus under root of mu. So x2 these are my three fixed points, correct? Now coming on to, we want to know that what kind of a bifurcation is actually occurring over here. right? We are interested in knowing that what kind of a bifurcation is occurring. So first thing that is to be kept in mind is that where my roots will exist, right? So the first root is going to exist everywhere irrespective of the value of the parameter mu, correct? But the second and the third roots, they are going to exist only if mu is greater than 0, correct? Because if mu is less than 0, these two roots are not going to exist. I hope this is clear. So this will exist only for mu greater than 0. Okay, this is clear. Which means that now I have a clear picture that for mu less than 0, I have 3 roots. And for mu, sorry, this is for mu greater than 0. For less than 0, I have only 1 root. Okay, this is the thing that I know now. Now I will talk about the stability, and on the basis of the stability, then we can say that, okay, this is the kind of bifurcation that is occurring. So we'll first compute the Jacobian, wherein we will differentiate. We are going to get minus 3, 1 plus x square plus mu. Correct? This is going to be my Jacobian. Now, if first I consider the stability of minus 1. So for minus 1, Jacobian is nothing but mu. So what do I get to know? I get to know that if my mu is less than 0, right, my minus 1 is stable. But as soon as the mu crosses the negative side, it goes to the positive side, minus 1 becomes unstable, right? So x1, which is minus 1, is stable for mu less than 0 and becomes unstable for mu greater than 0. Correct? I hope this is clear. Now I'll talk about the other two roots, right? I'll talk about the other two roots. So my Jacobian for x2, which is nothing but minus 1 minus under root mu, it is going to be what? It is going to be minus 3, 1 plus minus 1 minus under root mu square plus mu, which is going to be the minus 1 and minus 1 are going to get cancelled. I'll have minus 3 mu plus mu, which is going to be minus 2 mu. So you'll see over here that x2 is stable if mu is greater than 1 and is unstable for mu not 1, it should be 0 for mu less than 0, right? Okay, so the picture is clear. They have opposite behavior. X1 was stable for mu less than 0, and this becomes unstable as mu gets greater than 0, and x2 is stable for mu greater than 0. Now J for x3, which is minus 1 plus under root of mu. So this is going to be the same actually. Right? It is going to have the same behavior like that of the x2, right? So now if I conclude that what is happening, I have one fixed point for mu less than 0, three fixed points for mu greater than 0. Further, my fixed point -1 is stable for mu less than 0, becomes unstable for mu greater than 0. And the two fixed points which exist only if my mu is greater than 0 is stable. So if you remember, such kind of a thing actually happens in case of a pitchfork bifurcation. Remember, we had 0 as stable, then we have two branches which become stable and the 0 becomes unstable, right? So this is nothing but the case of pitchfork bifurcation, that too supercritical, that too supercritical pitchfork bifurcation. Okay, so if you look over here, option B is the correct option. I hope this is clear. This was a very easy question, only it was looking very difficult because of the cube term. Okay, now coming on to question number 8. So we have an equation and we have to find out what bifurcation occurs in the system with the change of parameter. Okay, so it is clear that the parameter is R, right? And because X is our variable that is changing with time, so definitely R is the parameter. So we have to see that what kind of a bifurcation is actually occurring with the change of R. So firstly, we'll compute the fixed points. So we have the fixed point as X is equals to 0, and the other two fixed points are going to be nothing but, so this. Again, now if you see that, just by merely looking at the equation, there's one thing which is clear, right? That there is some kind of a pitchfork bifurcation. Because again, we are having three roots, right? And one root, which is X is equals to 0, is going to exist. Is going to exist. I'm not saying stable or unstable, is going to exist for every value of R. It is like independent of the value of R. But the other two roots actually depends upon the value of R. Its existence will depend on the value of R, right? So it is clear that this is the pitchfork bifurcation. But now coming on to which kind of a pitchfork, we'll do the further analysis. First is we'll write the fixed points. These are the fixed points, and we'll write that x1 and x2 will exist only if minus of 1 plus r, or we'll say 1 plus r is less than 0, or r is less than -1. Yes, because only if r will be less than -1, then only we are going to have a positive value inside the root, right? And then only x2 and x3 will exist. Now coming on to talking about the stability. We'll compute the Jacobian. Okay, we'll differentiate. We'll have 1 plus differentiation of first function into 1 plus x square minus rx into 2x divided by 1 plus x square whole square. This is nothing but 1 plus rx square minus 2 rx square divided by 1 plus So we are going to have the Jacobian as 1 plus okay, this is going to be my Jacobian. Now for x is equals to 0, j is nothing but 1 plus r 1 by 1. Okay, this is going to be this only, right? So if you see that for my x is equals to 0 to be stable, this should be less than 0, which implies r should be less than what? Minus 1, right? So my 0 is going to be stable only for my r less than minus 1, correct? It is also important that we remember the fact that my other two roots existed only if my r was less than 1, right? We did over here, no? My other two root existed only if my r is less than 1. So as far as I can think, if I find out the Jacobian of the other two roots, it should come out to be positive, you know? Should come out to be positive. Let us just try. Okay. So for these roots, r should be less than minus 1. So let r is equals to minus 2. Okay. If r is minus 2, then my x1 and x2 is going to be what? X1 is going to be minus of 1 minus 2 minus 1. Okay. So x2 will be 1. Yeah. Okay. Now I will try to find out the Jacobian. So j is going to be 1 plus r, which is minus 2, into 1 minus. I have x square 1 whole divided by 1 plus x square 1 plus 1. Doesn't matter, it will go to 0. So I'll have j as 1, right? And you see the value of Jacobian, it is independent of x2 and x3. It is going to be the same for x2 and x3 because you see over here we have x square, right? So plus 1 or minus 1, it doesn't matter. So Jacobian is going to be 1 for both x1 and x2, and 1 which is actually greater than 0 means x1 and x2 will be unstable. It will be unstable everywhere, uh, or should I say it will be unstable wherever they will exist. Okay, it will not exist for all values of r. It will exist only for the values of r less than minus 1, right? And for all those values of r less than minus 1, it is going to be unstable. But my 0 is going to be stable because already I have seen my 0 is going to be stable for r less than minus 1. For r greater than minus 1, it will become unstable. So now if I try to plot it, what will I see? This is my stable 0. This is my unstable. This one is nothing but r is equals to minus 1. And I have a two unstable branches. So this is nothing but a case of subcritical pitchfork bifurcation, correct? This is nothing but a case of subcritical pitchfork bifurcation. So this is a case of subcritical pitchfork bifurcation. I hope this is clear. Now we'll move on to question number 9. Do you have, okay, yeah, we have enough time, we can complete it. Okay. So coming on to question number 9. The following equation has which type of bifurcation? Okay. Again, the same thing we are going to do. We are going to find out my fixed points. 0, 0 is definitely going to be a fixed point. Other than that, I want to know which kind of a bifurcation is occurring. So we'll first just try to find out the Jacobian. Okay. So Jacobian, let this be F1, this be F2. So I have Jacobian as nothing but partial differential. So if I perform the partial differentiation, what is going to happen? I'll have mu Okay, so this is going to be my Jacobian. So before going into this further, I would like to bring on uh, the equations or the theorems that was taught in the class in order to find out whether Hopf bifurcation is going to happen in our system or not. So if you remember, there were three things that was important. First one was first one was that my function f at x naught and critical value of parameter should be is equal to 0. Okay, the value of f, which is nothing but x dot is equals to f, it should be 0 at the whatever is my fixed point and the critical value of the parameter. Okay, second one was nothing but if I find out the Jacobian, this it should have a pair of imaginary eigenvalue while all other eigenvalue have real part of the eigenvalue not equal to 0. So this was essentially a case of non-hyperbolic fixed point. Okay. And the third one was transversality condition, which meant that, for example, if for the critical value of my bifurcation parameter, if I have the eigenvalue of this form, okay, this is the equation of my eigenvalue, then the partial differentiation of my lambda should not be equal to 0. This is yeah, that was, yeah, transversality condition, which needs to be satisfied. So these three conditions were important for the dynamic bifurcation or the Hopf bifurcation to occur. Okay, so I'll try to compare my equations with this. Let us see if the Hopf bifurcation occurs. So for the first case, f at x naught and mu c should be equal to 0. So see, if you see that 0, comma 0 is my fixed point, isn't it? 0, comma 0 is my fixed point, right? If I put those two fixed points in the equation, do you think that it matters what is the value of mu? Because mu is multiplied with x, mu is multiplied with y. If x is 0 and y is 0, it does not matter whatever is the value of mu, my f is definitely going to be 0. So my first condition is satisfied. Okay. I'll come to the second condition. which says that the Jacobian should have a pair of imaginary eigenvalues, while all other eigenvalues have a real part not equal to 0, which is the case of a non-hyperbolic fixed point. First, I'll be concerned about finding out the eigenvalues. Then we'll see na, that whether it is imaginary or not. So I have already calculated the Jacobian. I'll put x is equals to 0 and y is equals to 0. So what am I going to get? Mu minus 1, 1 and mu. Okay, this is what I'm going to get. Now if I want to find out the eigenvalue, what will I do? I will do j minus lambda I and I will take out the determinant. So determinant of mu minus lambda minus 1, 1 mu minus lambda. So you see plus minus, like under root of minus 1 is nothing but iota. So I'll have lambda as mu plus minus I. This is my I. Okay. Here I'll just change lambda to something else. Let us call it as phi, because then there will be a confusion. Okay. So this lambda is my eigenvalue. I have two eigenvalues and both are the conjugate pairs, right? We have a imaginary set. So now if I talk about the second condition, which says that for the Jacobian, there should be a pair of eigenvalues, like a pair of eigenvalues should be imaginary. Other eigenvalues, I'll just leave it because for now my equation is two-dimensional. So the maximum eigenvalue I'm going to get is 2. And if a set of imaginary eigenvalues is going to exist, both of them are going to be imaginary only. There's no other possible condition, because you know that imaginary eigenvalues are only going to exist in pair. Either there is going to be 0 imaginary value or there is going to be 2 imaginary value, right? Because it always exists in pair, 2, 4, something like that. But since my system is two-dimensional, so if there would have been no imaginary eigenvalue, then we would have cancelled it. Okay, there is a set of imaginary value. Rest of the eigenvalues, I don't care about it. Okay, because there is no eigenvalue. The system is only two-dimensional. So this condition is satisfied. Second condition is also satisfied. Correct. Now if I come on to the third condition, which says that for the critical value of mu, critical value is nothing but the critical bifurcation parameter, or at the point or the value of mu at which the bifurcation occurred, at which there is a change of the stability, there is a change of how the system is behaving, there is a change of number of equilibrium points, there is change of stability of equilibrium point. Whatever value of parameter at which this is occurring is known as the critical value of the bifurcation parameter. Okay, so it is saying that now if I have the root of like the eigenvalue, sorry, not root, eigenvalue of this type, phi plus iota omega. So if I am concerned only about the real part, if I am concerned only about the real part of my eigenvalue, the differentiation, partial differentiation of the real part of eigenvalue with respect to mu, which is my bifurcation parameter, it should not be equal to 0. Okay, it should not be equal to 0. So now if I come over here and if I look about at the real value, so real of lambda is mu, and if I do the partial differentiation, I'm going to get 1. Okay, and you see that this is independent of the value of the bifurcation parameter. Since I have to compute at see, this should be not equal to 0. Okay, sorry. at mu is equals to mu c. Mu c is mu c is nothing but the critical bifurcation parameter. Okay, so this partial differentiation should not be equal to 0 at mu is equals to mu c. So first we have to differentiate, then we have to put the value of mu c. Okay, so but in this equation or the eigenvalue that I am getting, we have the differentiation as 1 because it is actually not depending upon the value of mu. Okay, so it is 1 for every case of mu, for every critical case of mu, right? So like for example, if I have 1 for this particular equation, I'm not talking about, I'm talking about any different equation. So for that equation, if this is the case, then it means that if there are 3 4 critical values of bifurcation parameter, for all those 3 and 4 critical values, it is always going to be 1. It is never going to be equal to 0 because it does not depend upon the parameter mu. Okay, so now if I talk about the third condition, you see it is also satisfied. It is also satisfied. Okay, so now the question which is it is asking that which type of bifurcation is actually occurring over here. We know the answer. The answer is nothing but hop bifurcation. I hope this is clear. Okay. I hope this is clear why hop bifurcation is occurring, because you can see it simply that we have already satisfied the conditions, and that is why hop bifurcation is going to occur. There could be a case that why did we jump onto hop bifurcation? Why didn't we first write the conditions of static bifurcation, and then we would have checked, or we would have written both the conditions of static bifurcation and dynamic bifurcation. So for that, I'll try to give a rewind of the conditions of static bifurcation. So it had only 2 conditions. First one was the same, which said that f at x naught and mu c should be equal to 0. And the second one was, so second one was this should like it has one zero eigenvalue and other eigenvalues with non-zero real part, which was a case for non-hyperbolic fixed point. Okay, so we are not much concerned about hyperbolic or non-hyperbolic. What we are concerned about is that this was the condition for the static bifurcation. Okay, I didn't consider it because I wanted to tell you how do we do the conditions of Hopf bifurcation, but definitely when you have an equation, you should see both. You should see both which condition is satisfying. See, first one is the same for both. So first one you'll see, check. Second one you are going to come, you'll compute the Jacobian, you'll find out the eigenvalues. Now from this, the eigenvalues only you can differentiate now, right? Since there was a imaginary pair, so we then got to the third condition of the Hopf bifurcation. And if there would have been a case where we had zero eigenvalue, right, then we would have concluded, okay, this is a static bifurcation. This is not a case of dynamic bifurcation, right? So that is how it is. First condition is the same. So first condition, you are going to take it. Second condition, you are going to compute the eigenvalue. First, take out the Jacobian, compute the eigenvalue. From the eigenvalue, you are going to know that whether you have to go for the static case or you are going to go for the dynamic case. Okay, so here we can write Hopf bifurcation occurs in this case. Okay, I hope this is clear. Okay, now we'll jump up to the 10th question. Okay. Which of the following is going to affect the damping property with external stimuli? So see, in the class also it was discussed that there are different types of damping that can occur in a system, right? There was viscous damping, then there was Rayleigh damping, there was Coulomb damping. Okay. So, you know what is a viscous damping? So viscous or Rayleigh damping is nothing but where we say that my damping force is actually proportional to x dot, which is the velocity, and we say that Fc is nothing but c into x dot, where c is the constant of proportionality, and the variation is something like this with x dot. The variation is linear. So this is a kind of Rayleigh damping. We also define the Rayleigh dissipative potential on the basis of Rayleigh damping, right? So you see here there is a linear variation, right? And if I talk about it, does it get affected by external stimuli? No, it is not going to get affected by external stimuli. It purely depends upon the material constant, which we are going to get as the constant of proportionality. And it depends upon, like for the material property, it is going to be the same for the same material. Like if you consider a material and then you keep changing the loading condition and everything, the C is going to be the same. Okay. And if I talk about x dot, which is the velocity, so it will depend upon the velocity, but it does not depend upon any external stimuli. Okay, second, if we talk about the Coulomb damping. Coulomb damping is nothing but dry friction, which we have been studying since a long time in physics, where we have a mass which is kept on a rough surface, and now if I apply a force F on this mass, it has a weight mg, it has a normal force N, and we know N is equals to mg. So if I try to apply a force F in the forward direction, the mass is going to encounter a force at the surface, which is F, which is the friction force, which is equal to nothing but mu mg, right? It is going to be a friction force. There is going to be a reluctance. When you will try to apply the force, there is going to be a reluctance. The mass is not going to slip away, right? Because there is the non-smoothness in between the both surfaces. So we have a friction force which is equals to mu mg, right? Uh, actually, it should not be mu mg. It should be mu n, minus of mu n, and since in this case n is equals to mg, it is going to be minus of mu mg, right? In whichever direction you are going to apply the force, this friction is going to happen in the opposite direction on the surface. Okay, we have been studying it since a long time. Okay, so if I want to plot it, if I want to plot my force of friction with respect to x dot, so if my x dot is in the positive direction, the friction is going to act in the negative direction. If my x dot is in the negative direction, the friction is going to act in the positive direction, and its value is going to be mu n minus of mu n. Okay, so this is a Coulomb damping. So is it going to get affected by the external stimuli? No, it is not going to get affected by the external stimuli. Then we have the option D, which is MR based damper. So, you know, MR is magnetorheological, which is essentially used for materials which show the variation of properties or the variation of shape and size depending upon the change of the magnetic field, right? So what happens is that if you have you have particles that actually show movement or actually show some kind of a stimuli. If some magnetic field is applied, what is going to happen? These particles are going to align on the basis of the magnetic field, right? And on the basis of that, what is going to happen? There will be a change of the shape and size of, if I have an elastomer, then there will be a change of shape and size along with the change of the property. In case of MR based fluid, what is going to happen? There will be a change in the property of the fluid. So, MR based damper, it is actually known as adaptive dampers, and they are used in luxury car maker companies like, for example, we have Aston Martin. They use MR based dampers, to give adaptive properties to the damper. Because you see, if I have a damper with a fluid in it that does not changes its property, it will be good, for some kind of a terrain, but it may not be that good for some other kind of terrain. But in case of, adaptive dampers, our damper are going to change, the damping property are going to change, the material property or the fluid property are going to change, the viscous nature of the fluid is going to change depending upon the magnetic field that is applied across it, right? So what we can do is we can give a relaxed or a more better kind of uh, experience to the one who's driving the vehicle, right? So what happens in case of a MR based fluid or MR based elastomer, as we change the magnetic field, the magnetic field is going to change the direction of the magnetic particles. Based on that, the property of the material is going to change, the shape or size may change, and that would lead to what? Nothing but the change property. And that changed property we can further use, to give a better experience to the consumer or better experience as required, right? It can also be used, for vibration dampers, because, for vibration dampers, we have active and passive dampers. So for the passive dampers, we can use a spring mass dashboard system, but the mass is going to be constant, the damping is going to be constant, the stiffness is going to be constant. However, in case of active dampers, we can change the property of the material, and on the basis of that we can change the stiffness and the damping property of the material, which would be actually helpful for the active damping applications. Okay, so the answer of this is going to be MR based damper. Okay, uh, I hope this is clear. And this was it for today's live session. And I've discussed the question on the basis of the fact that whatever the questions were given in the assignment, you'll be able to solve it if you have gone through all this questions thoroughly. And rest, definitely, please attend the lectures. It will be good for you. And if you have any doubt, you can ask, or I'll just finish the session. Is there any doubt?
No, no.
Okay, then I'll end the session. Thank you for attending it, and we'll meet next week. Okay, thank you. Good night.